Okay, hello. So I'd like to talk about Entropy in the Second Law by Arieh Ben-Naim. Um, this is a book about entropy in particular and information, basically, information theory. It's very similar to this other book, Entropy Demystified, which is probably, I think, the first book of his that I picked up. Uh, Entropy Demystified is a little bit less quantitative, although it's still talking about the same things. So we aren't going to talk about this one, but this is another possibility if you'd like to see the same things only with less math. All right, so this is still a very good book, but I'm going to focus on entropy in the second law. Also, Naim has a book on the other side. He has actually several books on the same subject, but he has a book that's much more technical, if that's what you'd like, than entropy in the second law. Now, entropy in the second law is reasonably mathematical, right? So it's not super mathematical. The math is not everywhere. Oh, I shouldn't flip to that when I say the math is not everywhere. But the math is not everywhere, and you go long, long periods without any of it. And then you'll get into the weeds here and there. So you do need some mathematical background for this, but it's one of these strange books that are for people like you and me, right, who are perfectly comfortable with mathematics, but still want to read something that's not a textbook on a subject, want to read something a little more, uh, I shouldn't just say popular, but a little more qualitative in nature, but with some math in there to make sure that everything's well specified, right? Because that's what math really does, is it specifies what you're talking about in a more, um, oh, it's quantitative, but in a clearer manner than words do, a less ambiguous manner than words do, uh, if you understand the math. If you don't understand the math, then it's something that is going to distract you, and you have to either learn to read around or not read at all. But the math is in this text, and it will help you to be able to understand the math while reading it. Again, if you are really scared about math, you don't really love math, Entropy Demystified is a good book instead. Good alternative. And it's about games, so who doesn't love games? So lots of people don't love games. So this book is about the interpretation and misinterpretations of entropy in the second law. We'll get to those right away if we go through the table of contents, which is basically what I do here. And that's what I'm going to do here. I'm going to go through the table of contents and look at some of these things. And hopefully I can remember all these things, even though I only reread this for about an hour and a half or so. So how does this start? First, this starts with the macroscopic formulation of the second law of thermodynamics. That's where entropy is going to come from. That starts with Carnot, as you probably remember from your high school physics. And Carnot then is supplemented by Clausius and Maxwell, because Carnot's formulation is really just talking about the efficiency of heat engines. That doesn't get you a law of thermodynamics, but when Clausius goes through and tries to integrate that in, he gets a second law of thermodynamics, and we're good to go. We have a macroscopic view from measuring things with temperatures and volumes and things like that. That's macroscopic. I have a gas, I have a fluid. I can measure its volumes, I can measure its temperatures, and that gives me the second law. Then we go down to the microscopic definition of entropy. This is Boltzmann. So now we're going to go down and get into the weeds. So this here is the macroscopic formulation from Clausius, where a heat change is associated with an entropy change. So when heat is being transferred at a particular temperature, the entropy change is dq over T. But in the kinetic theory, when you have a gas, something like this, you have the entropy being equal to this Boltzmann constant, which is measured in joules per Kelvin, right? This is the transformation between um, temperature and energy, right? The energy in the mean molecular kinetic energy and all that stuff. And W is sort of the number of ways you can end up with the same state. So these microscopic configurations up here, you see they're all different. They have the same variables associated with them. They have the same number of particles. They're in the same volume. They have the same internal energy. So the number of these different pictures you can produce is basically this W. This is your sort of your partition function, we'll say. And that's a number of different ways you can do something. So this is what Boltzmann gives us, and he gives us that in sort of a classical statistical mechanics setting. Later on, but probably not here, that's going to turn into a way you can put quantum mechanics into statistical mechanics is through that W there. Then we have this wonderfully titled section, The Relentless and Never-Ending Search for a Simple, Intuitive, and Qualitative Interpretation of Entropy. And he's got 3 sections here. He's actually talking about more things in the text. But, your first one is order and disorder, right? Is entropy is entropy disorder, right? The answer is no, entropy is not disorder. Now, in some senses, in some places, it has a kind of sort of association with it, but they're not the same sort of thing. There are places where the disorder does not match the entropy, right? Order and disorder don't necessarily match. You've got things like solids where you end up with something extremely ordered, but they're in their maximal entropy state. So this association doesn't actually work. It's one way that some people have used to try to give us an idea about what that entropy is, but it's not actually disorder. The next one is with spreading, energy spreading, matter spreading, something like that. And again, that's not really the case. Remember, we were looking at those different pictures with those different particles in them, right? Spreading and dispersion are things that happen, and they're associated with an increase in entropy, usually. But, 1, not always, and 2, just because they're associated with them, it doesn't mean that they are the entropy, right? So there is something going on simultaneously in a lot of those processes where you have masses spreading out, you have diffusion, or if you have dispersion in the energy, where you have a highly energetic set on the right-hand side and a less energetic set on the left-hand side. I can't make both hands shake at different rates, I'm sorry. And then if these things are dispersing or shedding, they eventually end up with the same energy on both sides. Well, there are reasons for that. That does happen, but that is not, the dispersion is not driving the entropy. The entropy is not driving the dispersion, and it doesn't have to happen that way. And the association of entropy with information. Now, this one's a little bit less obvious that it's wrong, but what Ben-Naim is saying here is that we have a general idea of information. When you're listening to me, you're thinking about information in a particular way, right? How much information is being carried by my words, let's say. That is not the information necessarily that is associated with entropy. And we'll see that later on in chapter 4, maybe even here in chapter 4, I think, when Naim is going to use this statistic, or Shannon's measure of information, which is a statistical measure of information in the ideal gas. Okay, but this Shannon measure of information is only good for particular kinds of things, right? It's not good for every kind of information. And the ideal gas, we'll see, can be associated with that. But it's going to be sort of a subset of the statistical measure of information on that system. And Ben-Naim has a stringent test for the validity of your interpretation of entropy. And that validity is going to be that when a volume increases, I think it is, you get more entropy. When an energy increases, you get more entropy. When mixing occurs, you get more entropy. So basically he has 3 tests in that set. But in every single instance, you have to get more entropy. And that actually fails for all 3 of the things I talked about previously. There is a failure point for each one of those interpretations for the entropy. And you have to be very careful about how you talk about information for information to not fail this particular test. Okay, so chapter 2 is to start talking about statistical information. And I guess his paradigm here is the 20 question game. And how is the 20 question game going to do that? Well, what you're going to find here is that if you break up your questions perfectly, right? If you break up your questions so that every time you ask a question, you basically cut the space in half, right, into smaller and smaller chunks, moving towards your goal, that's when you get your statistical information. That's when you're going to get something that's similar to entropy. So let's see if we can find where he's got a very good picture of it here, right here. So you see, if you've got this 20 question game, right, you can see that, well, the 20 questions isn't going to be enough because you've got 8 possible things. But if you have 8 possible things, you could just ask a question to see if it's the first one, ask a question to see if it's the second one, third one, fourth one, fifth one, seventh one, eighth one. That's a bad strategy, right? Because you could ask a question that cuts the groups in half, possibly. The perfect question will cut the groups in half, 1 through 4, 5 through 6. Then you cut it in half again, right, with your second question, 5 and 6 versus 7 and 8. And then you cut it in half again with your third question, 7 versus 8. And you get 7 here in 3 tries. Here you might get 7 in 7 tries. Okay, so that's the worst case scenario, but that's basically what we're talking about. You know, obviously you could get it right just by luck on the first try. But in the worst case scenario, this strategy would take you 7 questions. This strategy would take you 3. So the entropy here in this set of 8 different possibilities would be 3, because you have 3 questions you have to ask. Even though you could ask in a stupid way, the entropy is 3 because it's the best strategy. So that's what he's going to talk about. That's the Shannon measure of entropy in a really neat nutshell. Actually, we should look at the definition itself here real quick. And see that this is the Shannon measure. H is equal to minus k times the sum of p log pi. And then you take a peek back here at what we were looking at for the entropy previously. S equals k log w, right? This is a particular case of it, and you see how close these are related. And that's the reason why we get this idea that entropy is a kind of information. Because entropy has these 3 properties, it's continuous in the probabilities. It's, you know, we've got an equipartition here. There's an equipartition theorem in statistical mechanics. And if you add 2 things, if you add 2 entropies, if you add the entropy of 2 systems, then you end up with a sum of those 2 systems as the entropy. And that gives you this same idea here, right? So these postulates give you this definition of something that we're going to call entropy, or the Shannon measure of information here. Um, Shannon didn't originally call this information. First, he called it uncertainty because he didn't want to use information because information was too broad. And then I think it was von Neumann told him, you know, you should uh, you should call this entropy because it has the same form. It has the same mathematical form as the entropy, and no one knows what entropy is. So as soon as you say that this is the entropy, they'll all shut up. So that's basically the Shannon measure of information. We saw that game here, so we have all these different regions. But here's a look at it again. We have this game here again, showing how we break this up for these different distributions. Okay, so then we go into um, entropy of an ideal gas, right? What are we talking about as the entropy of the ideal gas, indistinguishability of particles, which is something we talk about a lot in um, statistical mechanics. You actually, depending on if you have indistinguishable particles or not, you end up with different kinds of distributions, depending on whether or not you have, if you have indistinguishable or distinguishable particles, you have different distributions. If you have, there was another one that was important. Um, so indistinguishable particles means it doesn't matter when you pull out a particle from the distribution. You can't tell what order they came out in. And the other one is if two particles are allowed to be in the same state. So if you have a die, like this guy, if you have two dice, it doesn't matter what order you roll them in, right? It's six. It doesn't matter. They're indistinguishable as far as what we're doing is concerned. Actually, they are distinguishable. That actually could get me into a lot of problems. But in quantum mechanics, for example, they aren't distinguishable, so they actually get a different distribution. And if you do that different distribution, then you will get a if you end up with that different distribution, okay, I see it there, then you will get the way that Leibniz um, originally looked at the two dice game, and I got that from Ian Hacking's Emergence of Probability. It's a really good history book on probability. So if things are distinguishable or indistinguishable, that's important. If the order matters is important. If two things can have the same value is another important thing. So for dice, the two different dice can have the same value. You could end up with a 4 and a 4. But for a lotto game, for a Keno game, each draw is a different number, right? And so that gives you a different probability, which gives you a different amount of information. Okay, the momentum SMI, that's going to get you to your maximal Boltzmann distribution, which is so important. And that seems to be perfectly sufficient. Let's see. Then we have particular examples, the expansion of an ideal gas, mixing of an ideal gas, and assimilation of ideal gases. So these are three different particular situations in a gravitational field. You know, just different situations going through the same ideas, right, in chapter 4. So, you know, you end up with, you know, this expansion when you're going from just this small volume to this large volume. What happens to your entropy? Here you've got yellow and blue make green, right? You have yellow particles and blue particles, and they mix to make a green gas sort of thing for the mixing. And what's going on with the entropy, and what's going on with the statistical measure of the information as well. And so we get all of these things, the particular situations each. And Ben-Naim suggests at the beginning of chapter 4, try to do all of these things yourself because they're all very interesting. Last of all, he comes back to what's going on with the second law and asking each of these things, right? What drives the spontaneous process? Because people say entropy does, but entropy doesn't drive the spontaneous process. What happens there? Well, let's see. Wish I had more small little things. So let's say I've got a bunch of guys here, right? So there's a probability that, well, let's do 6, right? So there's a probability here, right, that one of them will move. 3 will move. And then there's a probability that the next one will move. 5 will move. So 5 moves. Then there's a probability another one will move. 4 will move. 4 moves. Then another one, 4. So 4 moves back. And then 6. 6 moves over here. And then 5. 5 moves back. 5 moves back again. And this is basically what's driving the spontaneous process, is that we have this fundamental randomness that underlies the system. And when things are moving from one state to another, they tend to move from a state that has less probability, like everything over here, to one that has more probability, which is 50-50. That's a highly probable state, right? And what's happening there? Why does it stay in this state? Why did it want to stick in this state? Well, the reason is because if there are more things on this right side, then when I roll the die, right, it's more likely that one of those guys is going to move over here, right? Although they were out of order, so this doesn't really prove anything. In this case, we'll get lots of fluctuations, which is what we ended up seeing, like that. But these fluctuations are going to be of the order 1 or 2 of these guys, but most of the time will be spent in one of these 3 configurations. Equal, 1 extra on either side, right? If I'd used an odd numbered die, which there aren't as far as I know, I could have done this in a way that it would stay in one of 2 configurations most of the time. And then when you have a large number of particles, when you have 10 to the 23 particles, then, those small fluctuations from side to side, they're just meaningless. So the spontaneous process just goes from an unlikely configuration, a configuration where things are more likely to switch from one side to the other, just because this one's more populated, to a more likely process. That's what drives entropy upwards, right? You go to a state where on 3 and 3, like this, then this is a possibility, this is a possibility, this is a possibility. There's just a larger number of combinations over here than there are for 5 and 1. Or 6, 0 and 6 is only one configuration. There are 6 different ways I can have one particle over here and so forth. So what's driving entropy upwards is the states that have the high probability are the ones that have this sort of equipartition going on. And because they have that equipartition, every time there's a fluctuation out of the highest entropy state, the next step is more likely than not to go back to the original state, the high entropy state. That's what's always going to drive it upwards. It's always moving towards an equipartition. Heat flow is associated with all of this as well. That's basically what's happening. Only it's happening in momentum space rather than real space. So physicists like to think about objects having a position and a momentum, right? So both of these guys have a position, both of them have a momentum. And as collisions occur between these guys, the momentum transfers and eventually evens out on average, right? And that's doing the same thing in momentum space. The energy is changing in momentum space in the way that position or location is changing in real space. So all of the same things that are driving um, things to be in different locations are happening for their momenta as well. And how did the system evolve? This is very important. Entropy had nothing to do with it. There are different underlying processes for different physical things. So if you have a electron gas, different things will happen than in a Bose-Einstein condensate, right? Different things are going to change how the system evolves because the statistics are different, because the physics of those systems, the microphysics, are different for those systems, and it's a microphysics that's changing things. It's a microphysics that's causing the evolution. The entropy, the temperature, these are macroscopic descriptions of what's going on in the interior, but they don't necessarily need to be part of that interior description. Second law in the arrow of time. Well, this is a big question, right? And Ben-Naim seems to agree with Boltzmann, which agrees with a lot of people, that the association of the second law with the arrow of time is basically because we are things that are, subjected to the second law of thermodynamics. We're moving forward because that's basically how entropy moves. So that's how it works, right? So what we see in the universe is based on the arrow of time, right? That arrow of time doesn't necessarily come from the second law, probably doesn't come from the second law. That arrow of time might have something to do with the microphysics, right? We may be in a situation like this, right? And we're moving towards a situation like this in the universe. But right now, that and that might be the reason. Now, that's not necessarily the only reason. People don't think that there could be many different rationales for the arrow of time. It's just that the fundamental physics is not affected by an arrow of time. Or the fundamental physics is time reversible, that is to say, for most situations. There are a couple of interesting situations that have to do with some K-mesons, I think, that don't quite fit a time reversible situation at the microscopic level. But the laws at the microscopic level are time reversible. And the most likely explanation for the association of the second law with the arrow of time is that we're in this giant space that is evolving towards a sort of universal entropy maximum, let's say. And because of the way we're built and because of everything else, we see the arrow of time at the same direction as everything else is evolving towards that entropy maximization. That takes us to this: does life emerge from the second law or does it defy it? And the answer here is no, right? That is, life doesn't emerge from the second law. Life emerges from the microphysics, let's say, chemistry, let's say. And so it doesn't emerge from the second law. That chemistry feeds the second law in a way, right, in the long run. But it doesn't, the second law doesn't cause life. Second law is something that describes a situation that life is sort of putting things through. Does it defy it? Of course, it doesn't defy it. The biggest problem here is that something that's living is not in a static situation, right? It's in a nonlinear thermodynamic situation, or not nonlinear, but it's in a non-equilibrium thermodynamic situation. If you're not in equilibrium, what does this entropy mean? The answer is it doesn't mean anything. No, maybe you can make something like it, but it doesn't have the sort of meaning that you'd associate with the statistical measure of information that we've basically said is a kind of the statistical measure of information, which is kind of a superclass that includes the entropy if you define your system correctly. So we have information, the statistical measure of information, what kind of information can actually be measured statistically, and then the entropy is kind of a subset of that if you put everything in the correct format. So put everything in the correct format, entropy can be a kind of statistical information, and that is a subset of all information in the universe. So that's a book. I like this. I like both of these books, obviously. I wouldn't have bought two if I didn't like them both. Uh, so I think they're pretty useful. Right? Yeah, the second law reduced to plain common sense with 7 simulated games. So some games to teach you what statistical mechanics is like. Very, very interesting books. So I think you might want to pick one of these up if you have any desire to learn a little bit about what entropy is. You see here, this dartboard is saying that disorder is not entropy, freedom is not entropy, spreading is not entropy, information is not entropy, chaos is not entropy. The statistical measure of information he puts on the bullseye of entropy. Is Ben-Naim the one who labeled this um, particular illustration? I don't know. I do not know if he did that, but I think they're pretty close. I don't know if you know we're talking to Ben-Naim if he would put these in the same order, right? He would say chaos is less good an description than disorder, which is about the same um, as order, which is both of which are better than freedom as a description of entropy. Spreading is getting pretty close, but not there, and SMI is dead on. I don't know if Ben-Naim um, illustrated this or put these labels on this thing to say which is a better descriptor of entropy or not. Just stick with the Shannon measure of information. That's what's going to give you the entropy. That's what you want to look at. All right. Again, I like these books. I think they're fun. Um, they're very useful for getting an idea about what entropy actually is. And so if you like these sorts of things, go ahead and take a peek.